All right, so guys, this is where we left off last time. So we're going to use this as sort of our connecting point. And don't let this be confusing if you're in lab. I know that we watched this video an hour ago talking about enthalpy, but guys, we can similarly use this video to talk about entropy. So, as we look at this video, guys, we said some interesting things about what was going on with disorder, which is entropy. So, guys, what we claimed and what we need to understand is there are ordering and disordering processes going on as we watch the video. So, guys, we talked about there being three processes. And as we talked about those, we identified whether disorder was going up or down. And remember, it's disorder, whether disorder was going up or down in these three processes. So, guys, where in this process of creating a solution, guys, where in this process is disorder going up? Go ahead, Doug. Good. So we've got this salt that is a crystal lattice. And guys, this is going to become important as we talk about what things influence entropy. Guys, crystals have amazingly low entropies. These things are very well ordered, so they have very low entropies. And as this thing dissolves and goes into solution, the entropy of the salt goes up. You okay with that? Okay, so guys, other processes here where entropy is going up, where the disorder is increasing. We good? So guys, where then do we have ordering processes? Where is the entropy going down, all right? Yeah, and we move forward to this, and we got the idea, guys, that we actually have a not offsetting, but a competing decrease in disorder. It turns out, guys, that the water molecules, the entropy of the water is actually going down because in the absence of the salt, the water molecules' locations are random, but as we then get these water molecules organized around the ions, their positions are no longer random, and therefore their entropy goes down. Go ahead.
So is it true that like entropy can go down, but like the net entropy of the process never goes down?
Yes, and that's what we're about to talk about. So guys, Susanna said something important. She says, is it true that there can be a decrease in entropy and yet a net increase in entropy, right? And the answer is yes, and it's the second law of thermo, which we're about to any process that takes place, entropy is always increasing. Understand, it may not be directly in the thing that you're observing, but if you're observing something and it looks like there's a net decrease in entropy, somewhere in the universe there's an increase in entropy. And we're going to talk about that more in a minute. So guys, you comfortable with what we're saying wrapped around this video? Okay, so guys, let's bring this together then, and let's take this to something that we can all agree on. So guys, this is where we should be right now. Did we get this in our notes last time? You guys are okay? So guys, entropy is the disorder of... No? So guys, let's go through this and make sure you're clear. So guys, the disorder of a system is what we call entropy. And guys, this is abbreviated S. So the accepted abbreviation for entropy, just like enthalpy is H, entropy is S. And guys, if entropy is disorder, and this is important relative to sign, if entropy is disorder, then the more disordered a system is, the larger the entropy of that system. Now guys, from that, we can then talk more about this dissolving salt in water process. And if you got table salt, by the way, in the lab, who got table salt? You're about to learn something. Guys, it turns out that dissolving table salt in water is actually an endothermic process. So, Remember what we said, endothermic processes tend to not happen spontaneously. Things that give off heat tend to happen spontaneously. So guys, dissolving table salt in water should not be a spontaneous process because it's actually a net energy gainer. In terms of heat, it takes in energy. But we know that salt dissolves spontaneously in water. And the question is, how can that be? If salt takes in water when it dissolves, then what is it that makes it spontaneous as it dissolves in water? Go ahead. In what form? Exactly. And guys, you got to understand this, that as we're thinking now, and this is going to come together on Thursday with Gibbs free energy, as we're thinking about driving forces that cause reactions to happen, we're comfortable with the idea that giving off heat makes things spontaneous because you can picture heat leaving. But guys, we got to get comfortable with this idea that disorder is a very real driving force in our universe. That things that happen spontaneously increase disorder, just like the dissolving of salt. Because relative to the heat exchange, it shouldn't happen spontaneously, but it does. And the reason that it does is because the disorder goes up more than the amount of heat that it gains. And we're going to quantify all of that when we talk about Gibbs free energy. But for now, guys, just understand, disorder is a driving force. Go ahead, Jeanette. Oh, absolutely. So Jeanette's question is spontaneity and solubility related? And the answer is yes, because when we talk about a salt that's soluble, that means that it dissolves spontaneously. And if we have a salt that doesn't dissolve, then it does not go into solution spontaneously. So then the question becomes, why wouldn't a salt dissolve? And most of the time it has to do not with entropy, but with enthalpy. You're going to find that heat exchanges are so much greater in magnitude than disorder exchanges. But typically the reason that a salt, let me go back to the video. Typically the reason that a salt won't dissolve, imagine that this isn't table salt. Typically the reason that a salt doesn't dissolve is because the ionic bonds that are inside the salt are so strong that you would have to add so much energy to get them to break apart that energy just isn't available. What you'll find out is there are actually some salts that are not soluble in cold water, but can become soluble in hot water, which kind of reinforces the idea, right? Because if you heat up the water, now the water has more energy to impart into the salt, and you can actually add enough energy that you can dissociate those ionic bonds and get them to dissolve. So, yeah. Mark, were you going to say something?
So, if entropy is such a small amount
Yeah.
of energy compared to
Yes. Uh-huh. No, it's actually the other, and that's a really interesting question. So Mark's trying, and this is what Gibbs free energy will let us do on Thursday. But guys, Mark's question, if I'm understanding you correctly, is if the magnitude of entropy changes tend to be in joules, small amounts of energy, and if the magnitude of enthalpy changes tend to be in kilojoules, large amounts of energy, does that mean that if you've got a process that's endothermic, that the amount of disorder created has got to be like crazy amounts of disorder to offset the enthalpy change? And the answer is no, it's actually the opposite. The systems that are endothermic that tend to then be spontaneous because of an entropy change tend to be only slightly endothermic. So if you were to look up, and John, this is going to make your guys' lab tricky. If you got table salt, this one's tricky. Because if you look at table salt when it dissolves is endothermic. The thing that we said that allows it to dissolve is the increase in entropy. But if you look up the heat of solution for table salt, it's bitty. It's like 1 or 2 kilojoules per mole. It's so small that the change in entropy can overcome it. So the answer to your question is typically that entropy enthalpy interchange, the entropy change can overtake the endothermic enthalpy change only if that enthalpy change is really small. only slightly endothermic. So guys, are we good? Are we feeling okay about where we are? This enthalpy, entropy, disorder. Okay. So guys, if we're comfortable there, what we now need to do is talk about how to quantify entropy. So guys, remember what we talked about heat. And we said that when we quantify heat, it's hard to measure the heat of a system, so instead we measure heat changes, right? Do you remember that? We said you can't like stick a heat meter or an energy meter into a substance, so instead we change the energy of the substance using heat, and then we measure the differences in temperature. Well guys, entropy is different. Actually, entropy is the opposite. It's hard to measure changes in entropy, so instead what we do is we actually figure out the entropy of systems, and many times this is computational or mathematical. It's not something we're going to do in lab. We just look these things up in tables. So guys, it's a minor point, but it's worth mentioning. Just this idea that when we talk about entropies, it's actually hard to measure entropy changes, so instead we measure the entropy of systems, and then we use that information to calculate the entropy changes. So guys, this leads us then to what are called standard molar entropies. This is abbreviated, as you might guess, S naught, where the naught means at standard conditions. And guys, the units are joules per mole Kelvin. So once you catch up to me there, we're going to talk about what all of this means. You guys okay? Y'all, or can we talk about this? Okay, so guys, the first thing that you'll notice is this. When we started talking about calculating delta H's, we talked about the idea that we talk about heats of formation. Remember the idea, it's the amount of energy gained or lost when a mole of a substance is created from its component elements. And we talked about heats of formation. Guys, these are not entropies of formation. So when you look up this data, don't get confused. This is not like a heat of formation. This is not the amount that the entropy changes when a mole of a substance is created from its component elements. These are not of formations. This is just, here's a mole of this stuff, how screwed up is it? Literally, and the thing that's interesting, guys, is we measure screwed up in joules. So you can actually quantify how disordered something, and you can measure the amount of disorder that a substance has in joules. But now notice this. Looking at the rest of the units, guys, what is disorder dependent upon given the units for disorder? Temperature and amount. So guys, let's talk about it. So if you've got 1 mole of something and you know how messed up it is, what its entropy is, what if you have 2 moles of it? Will its entropy be greater or less? Greater, twice as much. So guys, this is actually a value that scales with amount. So if you double the amount, you double the disorder, which kind of makes sense, right? But guys, it also scales with temperature. So what's going to happen to disorder as temperature goes up? Will it go up or down? Can you picture it? That as you heat something, those particles are moving faster and faster and faster and faster, and as they do, their disorder goes up. So guys, entropy, again, is measured in joules, and it scales with amount, and it scales with temperature. So the more of something you have, the more disordered it is, and then the hotter the temperature, the more disordered it is. Does that make sense? Okay, so this then leads us to some guidelines. Guys, these are the things that you need to understand conceptually. First of all, this, when we're dealing with entropies, unlike enthalpies of formation, guys, elements have disorder. So remember how we said that the heat of formation for the elements is 0? Well, guys, that is not true for the entropies of elements. Elements have disorder, just like compounds and everything else. Then, guys, thought number 2, this should make sense. The entropies of gases are greater than liquids, and those are greater than solids. You'll find more information on this in 19.3 if you want to look. Then, guys, guideline number 3 relative to entropy. Entropy tends to increase with greater molar mass. So the heavier a molecule is, the greater that its entropy tends to be. Then, guys, number 4, as we just said a moment ago, entropy increases with amount. The more of something you have, the more its entropy increases. Then number 5, entropy tends to increase with the number of atoms in a molecule. The more complex a molecule is, the greater its entropy will be. And then, guys, finally, number 5, entropy tends to increase with elongation. The more stretched out a molecule is, the greater its disorder will be. And guys, we're going to talk about this idea more when we start looking at intermolecular forces. Yep. So guys, what do we do then with all of this information? Well, we can actually, you're going to see conceptual questions relative to these things, but you're also going to see mathematical questions relative to calculating entropies for processes, entropy changes for processes. So guys, this is the equation that you use to do that. Just find it on the AP equation sheet, and then we're going to solve one of these. And then we're going to stop there and turn you loose on some of this homework and let you progress from there. So guys, notice again the difference between the equation that's in your equation sheet and the equation that's on the board. They don't include the n's, which are simply the numbers of moles of these things in the balanced equations. You just need to remember to include those. So guys, let's solve one. We'll wrap up from there, and then we will give you some time to complete this homework, look at another little bit of homework as well, and then if you want to use some of that time to work on your labs, you can as well. So guys, mathematically, you're going to see questions like this. It says, calculate the delta S for the synthesis of ammonia from nitrogen and hydrogen. Now guys, here's what we're going to do. We're going to tackle this from two different directions. We're going to write a balanced equation for this, and then we're going to talk about it conceptually, given the guidelines that we just looked at, and then we're going to figure it out mathematically and see if the math supports the concepts. So guys, the first thing we need is a balanced equation. You should be able to do that on your own. Write the balanced equation for the synthesis of ammonia from N2 and H2. So here's what we got. We've got N2, we've got H2, and then guys, we've got our product, which is NH3. Now to balance this, we need a 2 and we need a 3. And then guys, let's do this. Let's include subscripts on these. These are all gases. So our goal in this is we're going to figure out delta S for this process. Does entropy go up or down as nitrogen and hydrogen forms ammonia? But guys, before we figure this out mathematically, we're going to talk about it conceptually. So here's what I want you to do, and I want to give you a sense to really think through this. Maybe you need to look up in your notes and look at the guidelines. But guys, I want you to make an educated guess. And you should get in the habit of doing this, especially in the thermochem unit. Because guys, signs are everything, because it's up and down and in and out. And before you ever sit down to do computation, you should always be thinking to yourself, what kind of answer am I expecting? So guys, I'd like you to think about that. What should happen to entropy? Should it go up or down during this process? I don't want you to talk about it yet. Let me give you literally a minute by the clock to think about it. Then we'll talk about it corporately. But guys, the question is, what's going to happen to entropy, up or down? So guys, you've had about 30 seconds to ponder it. Now I want you to do is grab the person next to you and convince them that you're right. Go. Okay guys, you ready? You didn't necessarily need to agree with the person that you were talking with, but we're going to do this with thumbs. So up or down? What do you think? Will the entropy go up or down during the process? We got some ups, we got some downs. David, hang loose is not a vote. Up or down? We got up, we got up, we got a lot of ups, we got a lot of ups. Should we do the math first and figure it out or talk conceptually? Let's talk conceptually. So guys, I'm seeing a split in the room, but I'm seeing most of you saying that the entropy will go up. You may be interested to know that the entropy is going to go down. So now we need to talk about why. So guys, regardless of whether you got the question right or wrong, the question is, what was your reasoning? What were you drawing upon in order to come up with the conclusion, regardless of whether you were right or wrong? So guys, where did your brains go? Go ahead, Nathan.
I saw two things turning into one thing.
Okay, so we had two things turning into one thing, and if two things are turning into one thing, what does that make you think about entropy, up or down? Because there's fewer things? What else, Levi? Okay, so you said more atoms in the molecules? Is that what you said? Okay, so we have a more complicated molecule over here, which may cause the entropy to go up. And then Nathan, you're saying literally fewer things over here, so maybe the entropy is going down. Guys, other thoughts, other things that were driving your problem solving? Does that really encompass? Go ahead, Doug. Okay, which would make you think what? Okay, Go ahead. Say that again. Who's bonding? Okay. Interesting. So maybe there's an organizational process there. Other thoughts? Interestingly, none of you talked about phases of matter.
I was thinking that, but I was like, if they're all gases, would that make it like?
Go ahead. Finish. Yeah. Would it make it what?
I was thinking that because it was all gases, it would make. I mean, because it was a gas, it would make it go up.
Right.
But if they're all gases, would that make it go down?
Perhaps. But it is important to talk about, right? So, guys, I love the collection of thinking that you guys were doing in the room. You didn't talk about phases, but perhaps it's because it didn't change. We had people talking about molecular complexity. We had people talking about numbers of particles involved in the reaction. And guys, I love that you were trying to dig through those guidelines and find something that you could base your guess, your hypothesis upon. Guys, let me help you with this process, because this is something that they're going to have you do on the AP test. So guys, let's talk about, because they're going to ask you, and even on the test you're taking Monday, you are going to be given equations and given reactions, and you're going to be asked to predict, does entropy go up or down? So guys, let's talk about those predictors, and you may want to write this down somewhere in your notes. So what are the predictors? How do we use these guidelines to make predictions? Well, guys, the number one predictor of entropy change is phase. If you have a phase change, that will trump any other changes that you might be looking at. Guys, phase changes are huge changes in entropy. I mean, picture a solid that has a very low entropy melting into a liquid. Guys, entropy goes through the roof when a solid becomes a liquid. But then imagine when the liquid becomes a gas. Even more so, right? Those molecules are moving all throughout the room. So guys, phase changes trump any other change when it comes to entropy change. But again, as we noticed here, guys, the phase isn't changing. But let's pretend it does. Say that this, instead of becoming a gas, became a liquid. What would the entropy change be? Down, right? Entropy down. Crazy gas, relatively more organized liquid. Now, guys, what if it went the other direction? What if we started with liquids and then this became a gas? Then the entropy would go up, right? Now, guys, understand they wouldn't put you in this position. Well, they could put you in that position. But imagine if they did this. If this was a liquid, this was a gas, and this, so yeah, plasma. So imagine this was a solid, this was a gas, and that was a liquid. They won't do that to you. It'll be clear. So guys, our first predictor then is phase. And we're understanding that phase is not changing. So what then is our secondary predictor? Number of moles. Guys, our secondary predictor is actually number of moles. Which is kind of, Nathan, what you guys were sort of approaching, but not directly. So guys, the idea is this. How many moles of reactant gas do we have? 4. How many moles of product gas do we have? 2. But I don't want to discount what some of you were thinking, because you were thinking, yeah, there's fewer moles of product, but these molecules are more complicated. And while that is true, guys, the decrease in, or the increase in complication, because these molecules are a little bigger, is offset by the decrease in number of moles. So guys, your secondary predictor is the number of moles of reactant and product, and here the number of moles is decreasing, so that would be a decrease. That would be a decrease in entropy. And guys, frankly, on the AP test, this is where they leave this. They don't have you dig any deeper than this. Understand those other things that you learned in the guidelines we'll be drawing on later, but these are the ones that you need to know to predict changes in entropy. You need to know that change of phase trumps everything else, and then numbers of moles is a secondary predictor of entropy change. Is that okay? Okay, so now guys, let's do it mathematically. So let me erase all of this. And then guys, we're going to go back and we're saying now that the entropy change here should be negative. We should have a decrease in entropy. Now guys, let's do the math. So we need an equation. So we've got, right off the AP sheet, we've got delta S naught is equal to the sum of the entropies of the products minus the sum of the entropies of the reactants. So now we just need that table, which you'll find on page 801. And guys, you'll notice the table on 801 says standard entropies for selected substances. They give you the temperature. So we need nitrogen, and we need hydrogen, and we need NH3. So our product is NH3, so we're going to go 2 times, what is it, 190? 192.5? Why can't I find it? Oh, there it is. So 192.5, and that would be joules, minus the sum of 1 times the entropy of nitrogen, which is what? 191.5 plus 3 times the entropy of hydrogen, which is 130.6. And guys, probably we should be a little more careful and include moles and degrees, but we're okay. All right, so doing the math then, we have 192.5, multiply that by 2, and then subtract the sum of okay, what did I do? So guys, I'm getting negative 198.3 joules. Can anyone confirm that? Is that right? Go ahead, Jeanette. Yeah, so the units are joules, but they're actually technically joules per Kelvin. The reason is because these are actually numbers of moles, and the units for these entropies are joules per mole Kelvin. And so technically our moles cancel and we're left with joules per Kelvin. Is that okay? Go ahead, Emily. There aren't any. No, so should you be asked to do an entropy change calculation on an aqueous reaction that has spectators, you wouldn't see the spectators anyway, because it would always be based on the net ionic equation where you've already gotten rid of the spectators. Consequently, they're unchanged, so their entropy doesn't change, but we're just dealing with net ionic equations anyway. Is that okay? Yeah. Yeah, so how do they come up with these values? And it's actually fascinating. It's largely computational. that you can actually, there are equations that allow you to constrain the variables for a substance in such a way that you can figure out their entropies. It's based upon temperature, it's based upon all those guidelines, and you can actually take those guidelines and quantify them and then calculate these values. Understand, we can then come back and we can figure this out experimentally and verify them, but a lot of them are actually calculated. I'm sure that in college I was introduced to how they do it. I just don't, I don't remember, but yeah. So, guys, you okay? Are we good? Okay, and you'll notice that this does in fact support the idea that our entropy was going down, and again, we're attributing that to the fact that 4 moles are becoming 2 moles, decrease in moles, decrease in entropy. We okay? All right, so guys, this is where we're at then. Looking at the homework that we had previously, which was this. Some of these should have not been accessible to you based upon the fact that we hadn't put a tight point on those guidelines and a tight point on S. So you should be able to do all of these. Now this is where this gets weird, because also then, and I'll just have you write these down now. Guys, this is where the break got weird. Because this is the stuff that we just did, and typically I teach this the next day. But I wanted to bring this all together and wrap up entropy. So guys, writing down then this homework assignment. So we've got 7 and 8, and then skipping forward 45, 47, 49, 53, just A and B, 55, 57, 59A, 61 A and B, 65 and 69. What you're going to see, guys, is there's a break in this assignment. Some of this is about the math that we just talked about and the logic that we just covered. The rest of this is about Gibbs free energy and spontaneity. Guys, when you hit the Gibbs free energy stuff, stop. Okay? So what that means then, in summary, is do as much of this as you can, stopping when you hit Gibbs free energy, and then, what? Right under there. And then, guys, thank you. And then, guys, in addition, do as much of that. You should be able to complete this. Does that make sense? Okay. And then, guys, I will update the website so that you have access to all of this. Then when we get together on Thursday, what we will do is we will actually finish up with Gibbs free energy. That will allow us to complete this assignment. And then, guys, from there, the test will be on Monday. Go ahead.
So is Gibbs free energy like the delta G?
Yes, and that's where we're headed next. So guys, the remainder of the time is yours. Let's finish the previous assignment. Let's get to work on what we can of this assignment. If you need time to be wrapping up lab work, that would be fine too. We've all got plenty to do, so dig in, y'all.